Hello everyone. In this video, we're going to start talking about lesson 9, which is hypothesis tests and confidence intervals for mu. So you'll notice that in this video, or in these sets of videos, that the material that we're talking about is going to be very similar to what we've done in lessons 7 and 8. It's just that the symbols have changed, but nothing really else is going to change. So again, the material in lesson 9, which is this one, will be very similar to 7 and 8, okay, because we're working with hypothesis tests and confidence intervals. And hypothesis tests and confidence intervals are really the same no matter what we're looking at. So whether we're looking at proportions, which we talked about in lesson 7 and 8, or means, which we'll talk about here in lesson 9, the sort of machinery is going to be the same. It's just the symbols that we substitute in will be different. So if you found that lessons 7 and 8 made some sense, then this should be a quote-unquote walk in the park for you, because nothing is really going to change. And if you were on the other side where you struggled or found yourself struggling, then this is going to give you lots of opportunities to improve. So it works out for everyone. The most important piece of advice I'm going to give to you is to follow all of the steps that I go through. And so you'll notice, or you have noticed, that on your midterm, if you followed all the steps through, you did very well. If you didn't follow the steps, then you didn't do very well. So make sure to follow with all of the steps that I go through. And I do those steps to help you and give you a sense of what I'm looking for, and to give you the steps that many people like in a mathematics course. Although I don't love doing all the steps, I know it helps you out, and also most of the steps that we go through are actually important in doing statistics in real life. And so I'm not just making this arbitrarily challenging or hard, or at least I'm not trying to. But I do it for a reason, and hopefully you don't hate me for it. But if you do, that's okay. I have thick skin. So let's move on, and we'll first talk about a confidence interval for mu. And so I'll skip the sort of motivation stuff that we did in lesson 7. And if you are confused or you haven't thought about confidence intervals in a few days, and so you're rusty, I implore you to go back and look at lesson 7. So for a confidence interval for mean, we're going to start off with the same general formula that I started off with for a confidence interval for proportion. And that is a point estimate plus or minus a margin of error. So again, I'm going to start with, I'm interested in estimating some value that I don't know. And so what I do is I take data, okay, and then use that data to get myself a range of plausible values that value that I want to know something about is hopefully in, okay? And so what I'm going to do is start with my best guess, called the point estimate, okay, and then I'm going to add and subtract how uncertain I am about where that value could be. And so that uncertainty is in the margin of error. Okay, and so you'll remember that we break the margin of error down farther into two different things called the confidence factor and the standard error, and we'll get there in just a second. So what we're working with here, the population parameter, which we're interested in estimating, is mu, the population mean. Okay, and so here we're interested in estimating the mean of something. So maybe it's the mean housing price in Shippensburg, or the mean amount of time it takes for people to run a half marathon. Or there are many examples that actually matter to you in real life, but you have too wide a range of interests for me to list them, or I'd be listing them for 20 minutes. Okay, so we're interested in some value that we don't know, the population mean, okay, and we're going to estimate that. So we start with our best guess, the best guess for a population mean, okay, I have some population that I can't fully grasp. Okay, I can't take data from all of the population. Maybe my population is the whole United States. Okay, I can't do that. I can't find the mean of something about the whole United States. So what I have to do is I have to take a sample, and then my best guess at the value of the population is the exact thing, the mean of the sample that I took. So the point estimator, my best guess, is the sample mean. Now, as you remember last time, and from lesson 6, is that an important part of making a confidence interval is understanding how, and I say this a lot, hopefully it makes sense, but how X bar behaves, okay? And again, I'll reiterate, when I mean that, whenever you take a sample, okay, or think about taking a bunch of samples, okay? So I go out there, I sample 100 people. Great. I calculate that mean of the 100 people. I go to the next 100 people that I sample from that same population that I took the other 100 from. I probably am not going to get any repeats, but I could in my sample, okay? And so I take those 100 people, the next 100 people, and I calculate the sample mean for them. And I do that a bunch of times. You'll know, or you know, that the mean is not going to be the same for each sample that I take. And so it varies. We need to understand how it varies, and how we do that is with the sampling distribution, okay? And we found that in lesson 6 that the sampling distribution of X bar was normal. So X bar, the distribution of X bar is approximately normal with a mean of mu and a standard deviation of sigma, which is the population standard deviation, divided by the square root of n. Okay? So hopefully you remember this from lesson 6. Right? And of course, that sampling distribution depends on the sample size. Okay, it also depends on the population distribution of some sort. Okay, we really didn't go over that in lesson 6, but there are certain cases where it does. And what I mean by that, I mean how the population is distributed. Okay, or how the population behaves. But for us, we knew that n has to be greater than or equal to 30 in order for this sampling distribution stuff to behave. Okay, and again, a short side note: why that assumption is important is that if it's less than 30, then the distribution or how X bar behaves may not be normal. Okay, it may look may have a weird shape. Okay, that's not normal, and so we set that assumption is there for a reason. It's not just some arbitrary thing that I make you, some arbitrary hoop that I make you jump through. It's there for an actual reason. All right. Okay, so now we actually get to the confidence interval. So we have our point estimator, we have the distribution of our point estimator, how it behaves, okay, and that's enough for us to make a confidence interval. And so here's almost the confidence interval. It's not the actual one we're going to work with because there's something I have to talk about first, but this is the logical next step. The point estimator X bar plus or minus the confidence factor, which is a z-score. Again, it's that z sub alpha over 2 that hopefully you're getting more comfortable with, times the standard deviation of the sampling distribution. So I put that up in the right-hand corner here for you to, just for your reference, okay? And so I say that it's the confidence factor times the standard error. And the standard error, at least we can think of it as just a fancy word for the standard deviation of the sampling distribution. So over here. Okay, so there's our formula. Not too bad. It's pretty similar to a confidence interval for P, but of course I just have put in different symbols, okay? But there's a problem. Just like we had a problem, if you remember, with a confidence interval for P. I didn't know P, and so I had to substitute in the sample proportion P hat, okay? Well, of course, I don't know the sample mean mu, okay? Because if I did, I wouldn't be making a confidence interval for it. But that's okay because mu is not in the confidence interval formula, so that doesn't bother me. But what is there that is troublesome is sigma, and sigma represents the population standard deviation, okay? And so you have to think for a minute, if I don't know mu, the population mean, how likely is it that I'm going to know the population standard deviation? And so to give you sort of a concrete example of this, if I was really interested in the mean housing price of houses in Shippensburg, how likely is it for me to be able to say that I don't know what the mean housing price is, but I do know that the housing prices are spread out with a standard deviation of 1,500. Okay, in some ways, you need sort of more information about all of the housing prices to get the standard deviation. Not really. You just need the values, and you could get the mean and the standard deviation. But to really know the shape of the distribution, it's unlikely. So, all that being said, it's unlikely that you know sigma when you don't know mu. Okay? The two go kind of hand in hand. So I've got to do something about it, just like I had to do something about P before. So what I do is I estimate, or I substitute in the sample version of it, which is S. Okay, so that's just what I did with P and P hat. Now I'm doing with sigma and S. Okay, so instead of sigma in that formula above, I put S. Okay, and that's exactly what we did in lesson 6, and everything went just fine. Now, when we do that here, something different happens. Okay, behind the scenes, if you do like very high level math, something happens with the mathematics behind this formula. Okay, when I estimate sigma with S, meaning I put S in that formula, the distribution that we use to create or to find that confidence factor is no longer normal. Okay, so that means it doesn't follow that model that we talked about and called normal. It changes to something called a t-distribution. So now I'm introducing another model that your data could follow. All right? So we have the normal distribution, but there are others. And the other that we're going to talk about here is the t-distribution. Okay? Now, my very short little history story is that the man who came up with this, okay, so someone found this to be true in the early 20th century. His name was William Gossett. Now, I'll give you a reading here in just a second, and on the last page of that reading, they talk about this guy, okay? His name was William Gossett, okay, and he worked at the Guinness Brewing Company, okay, and he was working there as a chemist and a quality control officer, okay. He was very important to Guinness Brewing because in those days it was very hard to make consistent beer. Okay, when you made beer from batch to batch, it could vary in taste, in all kinds of things, because of course they made it by hand and not with machinery that can regulate all that stuff. And so quality control was very important to them because if they could make a consistent beer, they would beat all the rest of them. And they were able to do that, okay, because of William Gossett, who was a chemist and an early statistician, okay. And he found this out, and he eventually published a paper, but they wouldn't allow him to publish, and under his name for various reasons. And so his pseudonym that he used was Student. Okay, and so this distribution, this T distribution, is often called Student's T distribution, named after William Gossett. Okay, so that's my mini history lesson. If you don't like history, then it's okay, it's over now. And if you do, you can look up William Gossett some more. Now, a little bit about the T distribution. It's a continuous distribution, just like the normal. Okay, it's very similar to the normal, but it has quote-unquote fatter tails. All right, and you'll see a picture in just a minute of what that means. So, properties of the T distributions. Just like the normal, it's symmetric and it's bell-shaped. Okay? And something that's different from the normal is that the T distribution is always centered at 0. So it means its peak is always at 0. Right? It's characterized, or what I call parameterized, by degrees of freedom. So this is also different. The normal distribution was parameterized by a mean and a standard deviation. The T distribution is parameterized by degrees of freedom. Okay? Degrees of freedom. We won't talk about what degrees of freedom means in this context because it's actually quite complex. But we'll just know that I sort of input one value to the T calculator on StatCrunch, and that's how I distinguish between different T distributions. Okay, I denote it with a lowercase t. Okay, and then in the subscript, degrees of freedom. Okay, and also an interesting fact is that a T distribution with infinite number of degrees of freedom turns into a standard normal distribution. Okay, that last one you don't really need to worry about. Just some fun facts. Now, here's a picture of what a T distribution looks like against a standard normal distribution so that you can see what fatter tails mean. So you'll notice that the peak, it is symmetric and it's bell-shaped just like the normal. Its peak is going to be a little lower than the normal, okay? And if you look out here and here, you'll see that the red curve is higher, okay? And so that's what I mean by fatter tails. Okay, so now with our newfound information, the correct confidence interval for mu is this, okay? X bar plus or minus t, right? And t has the degrees of freedom that we're going to use here in the problem is n minus 1. N, of course, is the sample size, so it's a t with n minus 1 degrees of freedom. Okay, and we still have that alpha divided by 2 there to help us. Okay, so that's the same as the z-score with alpha over 2. We're going to do that the same way with the t-score, right? And so we have our full confidence interval there. So to get the confidence factor that we're going to need, we'll use StatCrunch, or if you're using Minitab, you can use Minitab. But it's going to be very similar to the normal calculator, and I'll show you in just a second when I go through an example. Okay. I'm also going to give you examples where you have actual data. Okay. And what I mean by that is I don't give you that the mean of 30 points was 5.4 and the standard deviation was 2.1. I'm going to give you those 30 data points. And when I do that, the entire process of creating the interval is going to be done with StatCrunch. That doesn't mean you can skip the steps. It just means that StatCrunch is going to be more a help more help to you than normal. Okay, so that's the confidence factor. The last part, okay, that's different from confidence interval for P are the assumptions that come along with creating the confidence interval. So the first assumption is the same as the last time, that the data is obtained by randomization. We always need a random sample. And then the different one is that here we want to know, or we want to assume, that the population distribution is normally distributed. Now, that is a hard assumption to satisfy, especially with the knowledge that we have right now. So, and you'll be a big fan of this, what we're going to do is we're just going to blindly assume it and move forward. Okay? That doesn't mean that's how you do it in real life. Okay? And that's not really how we should do it in this class. Okay? And if we had a full semester, I would tell you about how you can sort of check that assumption if you have real data. If I give you summaries, you're just going to have to sort of believe it's true. Okay? But if we had real data, we could actually check that. And to be honest, and as you will read if you read the reading assignments, okay, the book will tell you that that assumption is actually not quite as important as maybe those other assumptions for the other confidence intervals were. Okay, again, sorry for the side notes. Let's move forward. So here's a quick example that I'll show you all of the steps that I expect you to do. Okay, and I will show a quick example of how to find the t value, or the t confidence factor in StatCrunch. So my example is about my dog Newton. Okay, I think Newton is really fast. Okay, Newton is a Great Dane American Bulldog mix. Okay, so Newton is really fast, and so suppose I'm interested in estimating the average time it takes Newton to run the 40-yard dash. Okay. So I take him out and I time him 30 times, him running the 40-yard dash, and I find that the average time it takes for him to run the 40 in that sample was 3.8 seconds with a standard deviation of 0.3 seconds. Find a 99% confidence interval for the mean time it takes Newton to run a 40-yard dash. Okay, so there are a number of things that you have to look out for in this problem setup. You need to decipher it and see what are the important statistics that we're going to use. But first, what is our parameter of interest? This is where it starts to get interesting, because when we talked about that, this first step for P, it was kind of obvious because we had one choice, and that was P. Okay, but on the final, you could have one for P or one for mu. Okay, and so you've got to make that choice. And so I ask you to do this first step, because it makes you think about what type of interval you're going to make. Okay, so here our parameter of interest is mu, and mu is the mean time it takes Newton to run a 40-yard dash. Okay, in reality. So the second step are the statistics that we need. Okay, and so first, the sample mean, x bar, is 3.8. The sample standard deviation, S, is 0.3. Also, I don't write it down here, but the sample size is 30. Okay, and so N would be 30. Alpha, which is 1 minus the confidence level, okay, 1 minus the confidence interval, confidence level, a 99% confidence, okay, so 1 minus 0.99 is 0.01, great, and so then that confidence factor is 2.756, and so now I'll take just a slight deviation from the slides here, StatCrunch, okay? And so to find that t value, I'm going to go to Stat Calculators t, okay? And so it looks very much like the normal here. And it asks you, instead of mean and standard deviation, just degrees of freedom. And so in degrees of freedom, you put the sample size minus 1. So 30 minus 1 is 29. Okay? And I'm finding, just like you did for the normal calculator, hopefully, okay, I'm looking for the area here. I don't know this value inside, but I do know that the area over here is 0.005. And so when I find that value, you'll see it's 2.756. Okay, and so that's how I got my t value here. There's the confidence factor. So you find that very similarly to a confidence interval for p. All right, just with the t calculator instead of with the normal calculator. Now, assumptions. Was the data taken randomly? You may argue no, okay, but he's a dog, and so nothing is really going to change anything that he does, and so it's safe to assume that the data was randomly taken. Okay, he might run 40 yards many times during the day, and I could randomly take them. Okay. And is the population normally distributed? Well, we don't really know, and we can't really find out. So we're going to assume and move forward. Okay, and so we do our calculation. Okay, 3.8 plus or minus our confidence factor 2.756 times s 0.3 divided by the square root of n, which was 30, so the square root of 30. And when we do that, we get 3.649 not 3.95. Okay, great. So there's the interval. Now, the interpretation. Okay, interpretation is the last step. The interpretation is always I am blank % confident that, and then you have some space there where you have to talk about the problem specifics, okay, is between the two numbers. So I am 99% confident that the true average time it takes Newton to run a 40-yard dash is between 3.649 and 3.95 seconds. Okay, and so that is a full confidence interval problem from you worked out perfectly. So whatever you do, follow the 5 steps that I have here. Okay, and you are almost guaranteed to get at least half credit on those problems. Okay, so here's a reading assignment, pages 354 to 362, and I have a your turn, of course. Okay, and so here's the your turn. Go through, try to solve it. Okay, and see what you can do. Don't be afraid to look at the answer key that I have posted as well. I'll see you next time.